Ya, Assalamualaikum warahmatullahi wabarakatuh. This is Muhammad Zikri bin Muhammad Zanis. Message number is AA190019. Okay, for this group project, I with Ahmad Ahmad and Muhammad Aziz as a group. I will provide this bipolar junction transistor BJT. Okay, first of all is introduction. What is BJT? BJT is a three-terminal semiconductor device. The name bipolar comes by the fact that this type transistor contain two types of semiconductor material, P-type and negative type, triggered by current flow. P-type layer in BJT is to attract the electron that enter the transistor through the input circuit, and type layer encourage electron to flow out of the transistor. Okay, BJT is invented by physicist William Shockley in 1947. BJT has gone through the number of iterations over the years until the 1916. Germanium was used in the layer and then replaced by the silicon. Okay, what is structure of BJT? A bipolar transistor consists of three layers of sandwich of doped semiconductor material, or either PNP or NPN. Each layer forming the transistor has a specific name, and each layer is provided with a wire contact for connection to circuit. The function different PNP transistor and NPN transistor is a proper basic polarity of the junction when operating. Bipolar transistor work as a current control regulator, which restricts its amount of current passed according to a smaller control current. The main current is control goes to the control to collector to emitter or from emitter to collector depending on the type of transistor. The small current that control the main current goes from base to emitter or from emitter to base, and depending on the kind of transistor which is NPN or PNP. According to the standard semiconductor symbology, the arrow always pointing in the direction of current flow, as you can see in the diagram. Okay, bipolar transistor contain two types of semiconductor, which is P and N. As the main current goes from emitter to collector, two types of charge carry electron and hole comprise this main current through the transistor. Controlling current and the controller current always mesh together through the emitter wire, and their current flow in the direction of the transistor arrow. Small and the controlling current is usually referred to as simple as base current because it is only current that goes to the base wire of transistor. The large control current is referring to as a collector current because it is only current that goes to the collector wire. The emitter current is sum of base and collector current in conflict with Kirchhoff current law. Okay, what is operation of BJT? Okay, for this NPN transistor, the N-type emitter region has very high density of free electrons. Okay, next PNP transistor is a type is the P-type emitter region has very high density hole, and free electron from emitter region easily cross the base emitter junction and go into the very thin and lightly doped P-type base. The P-type base region is slightly doped because it do not have many holes. Only small percentage of free electron from emitter region can be combined with a hole in the base region. Okay, free electron from emitter region that recombine with the hole in the base region move through the base region as a valence electron. The free electron that enter the base region did not recombine with the hole move toward the reverse bias base collector junction. The free electron are attract to a positive side and are swept across in collector region. Move through the metallic collector, leak into the circuit and return into the emitter region. The emitter current is a sum of base of collector current. Therefore, the emitter current slightly greater than the collector current. Okay, for an PNP collector, PNP transistor, the role of electron and hole are swept. The internal bias voltage and the current direction are all reversed. Reversing the internal bias voltage with will forward bias. The base emitter junction of a PNP transistor reverse bias the base control junction, collector junction. The base emitter junction is forward bias. Hole in the emitter region can move through the base emitter junction and enter the base region. Electron in the base region can also move into emitter region. The emitter current is due to the movement of hole from emitter to the base current, but due to movement of the electron from the emitter region to positive terminal of the external bias voltage, the base current produced in PNP transistor is due to movement electron from external bias voltage into the base region. Okay, base region is a lightly doped. Only a small number of electrons in the base region recombine with the hole from emitter region, and the rest of the hole move into the collector region. This movement produces a collector current, but externally the collector current is the flow of electron from the external bias voltage the collector region. Okay, this is the direction current of NPN transistor as you can see in the diagram, and also PNP transistor. Okay, the flow of current in the PNP transistor is just opposite to the flow current in the NPN transistor. Okay, next is a configuration of BJT, which is 3 common base configuration with no current gain but voltage gain. Okay, the next one is common collector configuration, no current gain but no voltage gain, and lastly common emitter configuration with the current gain and voltage gain. Okay, for the common base configuration, base as the common terminal for both input and output signal. The input is applied between the base and the emitter terminal, and the corresponding output signal is taken between the base and collector terminal with the base terminal ground. Input parameter are V, EB and IE, and the output parameter is V, CB and IC. The input current flowing into the emitter terminal must be higher than the base current and collector current to operate the resistor. The output collector current is less than the input emitter current. The current gain is generally equal or less than 2 unity. The input and the output signal are in phase. And next one is the amplifier circuit called as non-inverting amplifier circuit. Common base region has high input independent and low input dependent. The voltage gain as current gain. The current gain is alpha is output current per input current. These are common base mainly used in the single stage amplifier circuit such as microphone, preamplifier, or radio frequency amplifier because they are high frequency response. Common base transistor circuit, as you can see in the diagram. Okay, this is input and output characteristic for common base configuration. Okay, for the input, this obtained between the input current and input voltage with constant output voltage. Okay, firstly, keep the output voltage constant to a vary input voltage. For different point, then at each point, record the input current value. Okay, repeat the same process at the different output voltage level. And lastly, plot the graph between input current and input voltage parameter. The equation to calculate is given. Input resistance value when input voltage is constant. Okay, for the output, obtain between output current and output voltage with constant input current. Okay, first keep the emitter current constant and vary the VCB value for different point and record current value at each point. Repeat the same process at the IE value. Okay, draw the plot between VCB and IC at constant IE. Okay, for the common collector configuration, it's made a collector terminal as common for the both input and output signal. Configuration: the input signal is applied between the base collector region and the output is taken from emitter collector region. The input parameter are VCB and IB, and the output parameter is VEC and IE. It has a high input independence and low output dependence. The input and output signal are in phase, and lastly, emitter current is equal to the sum of collector current and base current. Okay, for the current gain, you can get from this formula. And for this common collector configuration is known as Westin amplifier circuit. The voltage gain for this circuit is less than unity, but it has large current gain because load resistance in this circuit receives both collector and base current, like you can see in the diagram. Okay, meanwhile is input and output characteristic for the common collector configuration. Okay, for the input voltage I need to determine by formula and obtain between input current and the input voltage at constant voltage. Next you need to keep the output voltage constant at different level and vary the input voltage for different point and record the IB value for each point. And lastly, draw the graph between the parameters. Okay, for the output, obtain between the output voltage and output current as constant input current. If the base current is 0, then emitter current also becomes 0. If the base current increase, then the transistor operates with active region and finally reach the saturation region. To plot the graph, first we need to keep IB as constant value and will vary VEC or output voltage value for various points and record the value of output current for each point. Repeat the same process at the different for the different input current, and lastly plot the graph between the parameters. Okay, for the last common configuration, that is common emitter. Emitter as the common terminal for both input and output, and it inverting amplifier circuit. The input is applied between base emitter region and the output is taken collector and emitter terminal. The input parameter are VBE and IB, and the output parameter are VCE and IC. The emitter current is equal to sum of small base current and the large current collector current equal to IE equal to IC plus IB. The ratio between the collector current and the emitter current give current gain alpha in common base configuration similar to the ratio between collector current and base current give the current gain beta in common emitter configuration. The ratio between the current gain, as you can see, current gain alpha equal to IC per IE, current gain beta equal to IC per IB, and collector current IC alpha IE equal to beta IB. Okay, for the input and output characteristic, for the input they obtain between the input current and input voltage with constant output voltage. Okay, next you need to keep the output voltage constant, vary the input voltage for different points, and record the value of input current at each point, and draw the graph between the value. The equation to calculate the input resistance is, you can see, R in per VBE per IB when VCE is constant. What is output obtained between the output current IC and output voltage with constant input current. Keep the base current IB constant, vary to value of output voltage for different point. Note down the value collector for each point. Plot the graph between the parameter in order to get output characteristic. And lastly, the equation to calculate the output resistance from here you can get from R out equal to VCE per IC when IB is constant. This is just summary table for configuration. Okay, for this you can see voltage gain for base, common base is high, while for collector emitter low, and common emitter is medium, and net the current gain, power gain, input resistance, and lastly output resistance. Okay, that's all. Thank you. Okay, for the BJT, okay, for the bipolar junction transistor, we use the 2N3906 transistor. Okay, as you can see, this the data sheet for 2N3906. It's silicon. The connection is well stable for the TV and home, and small load switch transistor with high gain and low saturation voltage. Okay, this absolute maximum rating, collector base voltage, collector emitter voltage, and emitter base collector current, total dispensation, storage temperature, and main operation junction temperature. As you can see in this table. Okay, for the electrical characteristic, collector cutoff current, it has its value in this data sheet with and base up current, collector emitter, breakdown voltage, collector base breakdown voltage. Now for this mechanical data, as you can see, this is a diagram for transistor 2N59.6. Okay, that's all. Thank you.
Assalamualaikum and hi, my name is Malakwan bin Zulkifli from section 5, group 5 for electronic subject. So for this project I will present about junction field effect transistor or known as JFET. So structure of JFET. We saw previously that a bipolar junction transistor is constructed using two PN junction in the main current carrying path between the emitter and the collector terminals. The junction field effect transistor has no PN junction but instead has a narrow piece of high resistivity semiconductor material forming a channel of either N-type or P-type silicon for the majority carriers to flow through with two ohmic electrical connection at the end, commonly called the drain and the source respectively. There are two basic configurations of junction field effect transistor. The N are the N-channel JFET and the P-channel JFET. The N-channel JFET channel is doped with donor impurities, meaning that the flow of current through the channel is negative, hence the term N-channel, in the form of electron. Likewise, the P-channel JFET channel is doped with acceptor impurities, meaning that the flow of current through the channel is positive, hence the term P-channel, in the form of hole. N-channel JFET have a greater channel conductivity or lower resistance than their equivalent P-channel types. Since electrons have a high mobility through a conductor compared to the hole, the transistor makes the N-channel JFET a more efficient conductor compared to their P-channel counterparts. Next, for operation of JFET, biasing of an N-channel JFET. The cross-sectional diagram above shows an N-type semiconductor channel with a P-type region called the gate diffused into the N-type channel, forming a reverse bias PN junction. And it is this junction which form the depletion region around the gate area when no external voltage are applied. JFETs are therefore known as depletion mode devices. This depletion region produces a potential gradient which is of varying thickness around the PN junction and restrict the current flow through the channel by reducing its effective width and thus increasing the overall resistance of the channel itself. Then we can see that the most depleted portion of the depletion region is in between the gate and the drain, while the least depleted area is between the gate and the source. Then the JFET channel conducts with zero bias voltage applied, i.e. the depletion region has near zero width, with no external voltage or Vg equal to 0 and a small voltage Vds applied between the drain and the source. Maximum saturation current IGSS will flow through the channel from the drain to the source resisted only by the small depletion region around the junctions. If a small negative voltage or negative VGS is now applied to the gate, the size of the depletion region begins to increase, reducing the overall effective area of the channel and thus reducing the current flowing through it. A sort of squeezing effect takes place, so by applying the reverse bias voltage, increase the width of the depletion region, which in turn reduces the conduction of the channel. So next is for configuration of JFET. First configuration is common source configuration. In the common source configuration, similar to common emitter, the input is applied to the gate and its output is taken from drain as shown. This is the most common mode of operation of the FET due to its high input impedance and good voltage amplification, and as such, common source amplifiers are widely used. The common source mode of FET connection is generally used audio frequency amplifiers and in high input impedance preamps and stages. PN amplifying circuit, the output signal is 180 ohm out of phase with the input. Next is common gate configuration. In the common gate configuration, similar to common base, the input is applied to the source and its output is taken from the drain with the gate connected directly to ground or 0 volt as shown. The high input impedance feature of the previous connection is lost in this configuration as the common gate has a low input impedance but a high output impedance. This type of FET configuration can be used in high frequency circuit or impedance matching circuit where a low input impedance needs to be matched to a high output impedance. The output is in phase with the input. And finally is common drain configuration. In the common drain configuration, similar to common collector, the input is applied to the gate and its output is taken from the source. The common drain or source follower configuration has a high input impedance at a low output impedance and near unity voltage gain, so is therefore used in buffer amplifiers. The voltage gain of the source follower configuration is less than unity, and the output signal is in phase 0 ohm with the input signal. This type of configuration is referred as a common drain because there is no signal available at the drain connection. The voltage present plus VDD just provides a bias. The output is in phase with the input. Okay, and I will show you the datasheet for the transistor I choose, which is 2N4341. So as you can see, this gate source or gate drain voltage is negative 50 volt. Gate current is 50 milliampere. Storage temperature range is negative 65 degrees Celsius to 200 degrees Celsius. Operating temperature range negative 55 degrees Celsius to 175 degrees Celsius. Okay, so as you can see, this is the IGSS for the 2N4341 is 0.1 microampere, so you can see there. And test conditions, VGS equal to negative 30 volt and VDS equal to 0. So for drain cut-off current, the current is 0.05 milliampere, and at the voltage is at negative 10 volt. Sorry, for the drain cut-off current for 2N4341 is 0.07 milliampere, and as you can see, there is a very characteristic for this transistor, which is we have learned is IGSS, VGSS, VGS, ID or drain cutoff, IDS and IDSS. Okay, I think that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hazi Ahna bin Rosni. My number matric is AA190712. Okay, this is my part and I want to present comparison and exercise as amplifier application. Okay, let's go. Okay, this is the first table, comparison table. Okay, we compare the bipolar junction transistor BJT with junction field effect transistor JFET. Okay, first we go to the definition. BJT stands for bipolar junction transistor, so it is a bipolar component, while JFET stands for the field effect transistor, so it is a unijunction transistor. Terminal. BJT has 3 terminals like base, emitter and collector, while JFET has 3 terminals like drain, source and gate. Operation. The operation of BJT mainly depends on both the charge carriers like majority as well as minority. The operation of JFET mainly depends on the majority charge carriers either holes or electrons. Input impedance. The input impedance of this BJT range from 1000 to 3000, so it is very less. For JFET, the input impedance is very large. Okay, type of device. BJT is current control device, while JFET is the voltage control device. For noise, BJT has noise, while JFET has less noise. And for frequency, the frequency charge of BJT will affect its performance, while JFET, its frequency response is high. Okay, next the second comparison table. Okay, we go to the heat. It depends on the temperature, while JFET, its stability is better. For the cost, BJT has low cost, while JFET has expensive cost. For the size, BJT size is higher and JFET is low. For offset, BJT has a voltage offset, while JFET does not have offset voltage. Okay, for output impedance, its output impedance is high due to high gains, while JFET output impedance is low due to low gains. For terminal, as compared with the emitter terminals, both the terminals of BJT like base and collector are more positive, while JFET drains terminal is positive and the gate terminal is negative as compared with the source. Another terminal is the base terminal is negative for BJT with respect to the emitter terminal, while JFET, its gate terminal is more negative with respect to the source terminal. Okay, and the last comparison table. For current gain, BJT has less current gain, while JFET has high current gains. For switching times, BJT is medium, while JFET is fast. For BS, BJT is simple, while JFET is difficult. Next, BJT use less amount of current, while JFET use less amount of voltage. Okay, for applicable application, BJTs are low current application, while JFET are low voltage application. The consume of BJT is high power, while JFET is low power. Temperature coefficient. BJT have a negative temperature coefficient, while JFET has a positive temperature of coefficient. For the voltage gain, it has a high voltage gain for BJT and it has a low voltage gain for JFET. Okay, for the gain, BJT gain is more while JFET gain is less. Okay, next, example of BJT and JFET types where the amplifier circuit are implemented in industry and market. Okay, let's go. For BJT, bipolar junction transistor, we can see it is a circuit. We have bulb, source, and switch. Suppose we had a lamp that we wanted to turn on off with a switch. Such a circuit would be extremely simple as in the figure below. Okay, this figure. Okay, for the sake of illustration, let's insert a transistor in place of the switch to show how it can control the flow of electron through the lamp. Remember that the control current through a transistor must go between collector and emitter. Okay, and after we change switch to the NPN transistor, BJT, we can get, since it's a current to the lamp that we want to control, we must position the collector and emitter of our transistor where the two contacts of the switch were. We must also make sure the lamp's current will move against the direction of the emitter. Arrow symbol to ensure that the transistor's junction base will be correct as in the figure below. Okay. For BJT, it also can be switched. Okay, next we go to for junction field effect transistor, JFET as an analog switch is shown in figure. You can see JFET also can be analog switch. When no gate voltage is applied to the JFET, VGS equal to 0, JFET become saturate and it behave like a small resistance, usually of the value of less than 100 ohms, and therefore output voltage become equal to Vout equal RDS divide bracket RD plus RDS ohms Vin. Since RD is very large in comparison to RDS on, so Vout can be taken equal to 0. When a negative voltage equal to VGS off is applied to the gate, the JFET operates in the cut-off regions and it acts like a very high resistance, usually of some mega ohms. Hence, output voltage become nearly equal to input voltage. Okay. Next is example of voltage divider biasing circuit. Okay, let's go. First is common emitter amplifier BJT. Okay, first we have to find the RB. RB is like this. Okay, 1 over 30 kilo ohms plus 1 over 20 kilo ohms, and then after we get the answer, we have to 1 over the answer, and then we get the 12 kilo ohm. For the VBB, 30 kilo ohms over 30 kilo ohms plus 20 kilo ohms, and then after we get the answer, we have to times 2.5 volts, and we got 1.5 volt for VBB. Okay, for EB, we use KVL. Okay, 2.5 is the source. VEB, like we can see, is 0.7, and we have to plus 12 times 10th power of 3 IB plus 1.5. Okay, we have to find IB, and VEB we already know is 0.7. Okay, we bring this IB to the front, and we got IB 20 microampere. Okay, for the IC is beta times IB, Okay, we know that we have got the IB is 25 microampere, and then for beta is 100. After 25 microampere times beta 100, we got 2.5 microampere for IC. For EC KVL, we use the formula. The source 2.5 equal to VEC plus 500 IC. We got the IC at the EB KVL 2.5 milliampere, and we put here. Okay, we bring the VEC in front, and we can see 2.5 minus 500 plus 2.5 milli equal to 1. And we got 1.25 voltage. Okay, since VEC equal or greater than 0.7 volts and IC is greater than 0, assumption of BJT inactive is justified. Base summary: VEC equal 1.5 volts and IC equal 2.5 milliampere, and IB is equal 25 microampere. Okay, next is common source amplifier JFET. Okay, first we can see this circuit. We have the JFET here. Okay, first we read first. Determine ID and VGS for the JFET with voltage divider biasing in the figure shown. Given that for this particular JFET, the parameter value are such that VD equal 7 volt. Okay, this is the formula how to find ID. We have to VDD minus VD over divide by RD. Okay, we know that VDD is source, and then minus 7, and the 7 volt already give, and RD is this 3.3 kilo ohms. That we got 1.52 milliampere. Okay, next calculate the gate to source voltage as follows. Okay, how to find VS? The formula is ID times RS. Okay, ID, we already get the ID 1.52 milliampere, and then times the RS 2.2 kilo ohm, and we will get 3.34 volts for VS. For VG is R2 over R1 plus R2 times VDD. Okay, R2 is 1.0 mega and R1 is 6.8 mega, and then we have to sum this value. We will get 7.8 mega ohm, and then to divide it, 1.0 mega ohm divided by 7.8 mega ohm, and times to VDD is 12 volt, and we will get 1.54 volt for VG. For VGS we use this formula. VG minus VGS equal 1.54 volt minus 3.34 volt, and then the VGS is negative 1.8 volt. Okay, that's all from me for my part, and thank you for watching. I hope you understand, and I hope you like our presentation. Okay, bye.